my presentation would be on feasibility of osteoporosis detection from electromechanical gram signatures using piezo-based variable devices. So this is a part of the work is a joint work involving IIT Delhi and the Indian Spinal Injury Center. So basically here the main materials which are used, they are the piezo materials. So piezo materials are called as smart materials. Smart in the sense that they exhibit stimulus response characteristics. If we apply a mechanical stress as stimulus, we see the development of charges and hence the voltage, and this provides us a measure of the strain. And conversely, if we apply electric field, we see the development of strains, and this is used for actuation applications. So we have the direct effect, sensor effect, and the converse effect, the actuator effect, and together there are numerous applications of these two effects in our day-to-day life, including the mobile phones, the igniters, so many other devices we use in our daily lives. So basically the electromechanical impedance technique is a relatively new technique, and it employs the piezo sensors both as sensors as well as actuators. So here what we do, we bond the piezo patch on the structure and then we excite it into vibrations by applying an alternating voltage source. So piezo starts vibrating, but in this process it interacts with the structure dynamically, and the structure also modulates the vibrations of the piezo patch. Not only that, it also influences the electrical circuit comprising of the piezo patch and the device. So what we do is, in this technique, we then measure the current flowing through the circuit, and once we have the current flowing through the circuit, we have applied a predetermined voltage, so we can obtain the admittance, which is the ratio of the current to the voltage. So it's basically inverse of the electrical impedance, and because there's a phase difference between the voltage and the current, so this parameter has real and imaginary parts. So here the piezo patch is acting both as sensor and actuator. This technique originated from the aerospace industry and it has come down to so many disciplines including biomechanics and various engineering domains. So here typically we are just showing you in pictorial form how the setup looks like. So here we apply voltage signal in a sweep fashion, that is, we sweep through frequency range and then we obtain the admittance measurements and we get a signature something like this. So here basically the signature is in the frequency domain. It covers a broad spectrum of frequencies and it's something like the frequency response function, which is a common term in the field of experimental model analysis. So essentially this is the governing equation, that here we have Z, the mechanical impedance of the structure, and this is a mechanical term, but it is connected to the electrical output in the form of admittance. So directly measuring the mechanical term parameter is quite difficult, but here indirectly we are measuring the electrical counterpart and we are using it. So here there are no limitations which are there otherwise in the mechanical measurement, because here electrical measurements are there. So here there are no frequency limitations or similar kind of constraints. So it's very good and very easy way of doing the measurements. So here essentially we are getting the conductance and the susceptance signatures, the real and the imaginary parts, and conductance signature typically has peaks like this. Susceptance signature is more used for the purpose of diagnostics, whether the piezo is working fine or not. So typically if we have a small damage, very small say appearance of hole, some crack, so the signature is very drastically changed, and this provides us a very sensitive measure of the damage. So typically I am just showing some of the results from the concrete, because concrete is something, it has characteristics like bones. So it is also calcium based, calcium silicate hydrate. So here we are showing you the signatures from two measurements. One, the baseline measurement, that is black in color, and the other pink one. After subjecting the cube, the concrete cube which I showed in the previous slide, to just 100 kilonewtons of load, so which gives a small stress, so it induces micro cracks. But we can see the change in the signature, and when we increase the load, we double the load, we see more changes. So the technique is quite sensitive in detecting cracks, and this is the case that when the cube was at the penultimate failure stage, so it provided a very drastic change in the signature. So this technique is essentially a signature based technique. So signature is like a fingerprint, and any deviation in this signature, that gives us that something is changing in the system. So now in the case of the biomechanical or biomedical engineering field, the interest came. So initially in 2013 we did experiments involving the damage in the bones, but in the medical sector the more interest is not in fracture detection but in fracture healing. So that we found that this is also feasible, that if we have the patient has undergone fracture, then it is possible that the reverse, so healing is a reverse of damage. So conventionally this technique is applied for damage detection, so the reverse process, that is healing, is also feasible. But then how do we bond the piezo patch on the bone? So that is impractical. Similarly, studies have been done by this group of faculty member. Ribola was the researcher, and Rizzo is the faculty member at the Georgia Tech in USA, and they applied it for dental implant monitoring, the healing. And then here the issue is that if we directly bond the piezo patch on live subjects, it's not possible. So one important point is that we should have a non-bonded configuration, that is one part, and the other part is that we should have reference-free diagnostics. Typically you must have seen that we are comparing two signatures, one for the baseline and other after some time when we want to know the condition. But this is also not possible in the medical sector. Patient comes with some defect, so he does not have any baseline or the reference signature. So these two issues were addressed as part of the PhD thesis of Dr. Shashank Srivastav. That work we started in 2013, and so we devised this kind of non-bonded configuration where the piezo is separately bonded on a strip, and the strip is sort of connected in a non-bonded fashion to this artificial bone. So we performed the experiments, and we found yes, this is also yielding good results. It showed excellent repeatability, and we could very easily correlate the frequencies, the various peaks, with the actual modes of vibration of the bone, and this set the stage for the reference free or the baseline free measurements. And then we did damage in artificial bone by means of degradation. Very simple, these were the preliminary experiments. So we just used methyl ethyl ketone solution to cause degradation in this artificial bone, and we could get meaningful results. So once we had the initial experiment successful, we went further and we thought of detecting osteoporosis, and our impetus was always to get something in a baseline free manner. So here we are comparing two bones. One again, this is made up of plastic type material, so artificial, and here this is the osteo bone and this is the healthy bone, and we could get the difference in the signatures. And then we also did experiments with simulated skin. Here we have used silicone rubber for that purpose, and at the end we extended it to a live subject to check the feasibility, and it was coming out to be feasible. So here we then went further, that just signatures themselves, they are not enough. So if we make use of the equation, and then we just get from the electrical parameter the conductance signatures, if we are able to derive structure related direct information, then that would be better. because then we could do a sort of system identification. So with this intent, we went in the case of the bones also. For example, here this aluminum block, from the signatures we have identified it as a combination of spring and damper. Of course, I am not going into the mathematics part, just in essence this is how we do. And this is for the case of steel joint which we were testing, and here the system is identified like this, and the identified parameter stiffness, it shows sensitivity to the damage. So similar thing we identified for the case of the bones, and we found that healthy bone, it is identified as this series spring mass damper system, and the osteo bone we found it's identified as a different system. And we did a numerical simulation also to further see the results, and numerical simulation also showed this. So these are the results, one in the lab based specimens, other numerical models, but then this was not enough. We have also our idea we have patented, and luckily we came in touch with Dr. Shakti Goyal, Dr. Sunil Sharma and Dr. Chavda, and then our joint work started. When our collaboration started with the Indian Spinal Injury Center, then we thought that let's go further, and with their collaboration we started doing the test. And what we found that clamp had some effects, or it was not easy to sustain the clamps, so we switched over to this kind of flexible kind of grip, and we obtained signatures of 4 healthy subjects. They were volunteers from the army, and what we found, correlation, this is with the help of ISIC we did DEXA scanning, and I'm just hiding the names of the subjects, but they are all healthy subjects with very good bone mineral density and good T-score. And the common thing for all these subjects was that the system was identified as a series KMC system. And then after the lockdown we came in touch with ISIC again, and it's here that we collaborated with Dr. Jitesh, and we did some experiments on the osteo subjects also. And here we obtained basically four subjects were there, and these typically had lower bone mineral densities and the T-score. And we are in the process of analysis, and we have successfully analyzed 3 out of these 4 subjects, and we could see common trend here also, that here in fact the nature of the signature is a bit odd, and here the system identified is this parallel spring damper system. So consistently we observe this. If you can see, the plots are more or less similar in all the 3 subjects. 4th one we are still analyzing. So basically the conclusion is that here in brief, the EMI technique is successfully proposed as a credible bone diagnostic technique. It is shown in a baseline free mode, and then the results so far, they show that there are credible differences between the nature of the signature in terms of the impedance based identification for the healthy and the osteo subjects. So more studies are again needed. We'll collaborate further, because here in principle we are able to distinguish the 2 extremes. One extreme is healthy and highly osteo, and in between we need to do more experiments and do calibration and collaboration. So these are some of the references, and in fact you can also refer to our book, which is available in Wiley as well as in the Indian edition. Any books? So I think I have finished my presentation. I hope I am not too fast. So any queries you can always send me, and I think if questions are there, then I would be very happy to answer.